my first slide here is actually an optical picture taken from Hubble. And as you know, I mean, star formation is, you don't want to do the star formation studies in the optical because you don't see much. Because in fact, here, the star that is forming is in the darkest region. And so you need to have some kind of fantasy to actually see what's going on. So this is, you know, an artistic view. So you see these dark clouds where stars and planets form. I will review a little bit briefly because I'm sure Cecilia has done already the job, but just to put things in scale, etc. But yeah, everything happens in these very, very dark and obscured regions where yes, it's basically only with long wavelengths observations and say detailed also molecular observations, so you can actually go through and understand what is going on. So yeah, these are my first few slides, just a little recap on where these star forming regions are located. So I think this is one of the best way to see them immediately. For example, in our Milky Way galaxy that is here, this is the famous map of carbon monoxide done in 2001 of the whole galaxy. So you can see here that the red is the brightest part, so the region where the density is the highest, and in fact these are the regions, so yellow and red and also dark green are the regions where you have a lot of star formation going on. Star formation and molecules basically go hand in hand. That's why we use astrochemistry and molecules to study them. So you probably have learned that the molecular gas mass in our galaxy is about the same as the atomic gas mass, and this is of the order of a few times 9 solar masses. Also important to remember is that the dust to gas mass ratio is about 1%. So we have these tiny little dust grains that actually absorb all the light. And in fact, this is why these clouds are dark, but they're also playing a crucial role for the chemistry and also for, of course, building up planets, because they are the building blocks of planets. Most of the molecular gas in our galaxy, but also in other galaxies, are basically located in the so-called giant molecular clouds. They're giant because they're massive, so of the order of 10 to the 5 solar masses or more, and they are confined typically in spiral arms, in spiral galaxies like our own. And however, if we look at, so also inter-arm region, there are also small cloud and molecular cloud complexes, typically these are called dark clouds, that are only a few times 10 to the 4 solar masses. And these are the ones that are circled here in red. This is, for example, Taurus Aurigae, Ophiuchus, and Orion, and you see them up and down in the galactic plane just because it's a perspective effect that they are nearby compared to the rest of the galaxy. So, of course, molecules are extremely important because they tell us a lot about not just the density, the temperature, but also and probably mainly the kinematics. So we see, for example, if you take a pixel from this map of the metal, you see all these lines of CO at different velocity, and then you know that actually what you're not just looking at one cloud, but you're looking in this case 1, 2, 3, 4, 5 molecular clouds along the line of sight with different say abundances of CO or probably different densities. So you can really see through and reconstruct the model of the galaxy. So this is how you could see the Milky Way in optical, and then this is how you see it when you have CO. Of course, CO, the main isotopolog, is not so good to see the details and actually the regions of star formation. To do that, you have to go to rarer isotopologs. So in this case, here is a map of the 13CO, the gray scale here. So you start to see now the structure within this green region that in fact the 12CO is so optically thick, so abundant and so optically thick, this line, the 1 to 0, that you just see the skin of the cloud. You don't really see where stars are actually forming. But when you look at 13CO, things are getting better. You start to see substructure within the cloud seen in the 12CO. And then if you overlap the known, say, young stars on top of the 13CO map, these are the colored points, you start to see that there is a very good correlation between the region where 13CO is strong and the young stars. The pluses here, in case you're curious, these are more evolved young stellar objects like class 3 type of class 2 and class 3 type of sources, while here the color is more like class 1 or maybe just one of these class 0. If you choose even rarer isotopology, then you get rid of the extended emission. It's like an interferometer here. You get rid of all your extended structure, and you now focus on the filaments and the densest material. And in fact, with the C18O, you now get to know the filaments and clumps where actually star formation is actually happening. And in fact, with the blue dots here, I put the location of the famous ammonia cores. So these are the cores that were studied by Benson and Myers in the 80s, and with this beautiful summary paper of 1989, where they actually found that these are the units where stars are forming. So small region, but for this, you see, you have to change molecule because CO is not good at that. And we know that this could be another lecture on the astrochemistry. CO is actually starting to freeze out in these regions, and you have to change a switch to molecules, especially to molecules that contain nitrogen, that apparently are really good in showing the structure of this dense core. So if we zoom in, so now instead of few parsecs, we go to a fraction of a parsec, you can actually see structure of what we mean by dense core. So structures where you have, say, a few solar masses in and say sizes of 0.1, sometimes even less parsecs. And then a centrally concentrated structure where you actually have now started to see kind of a location where a future star could form. I wanted to mention that when you look at all these dense cores, so you will see dense cores that have stars. So these are the so-called protostellar cores. Others don't have stars. So some of these cores that don't have stars will make a star, some other will not. And so how do you distinguish these two? I mean, it's always very hard actually to know. I mean, it's probably impossible to really identify that a dense core will actually form a star, but we know that these are the units of star formation. So before the formation of the star, you have to have a dense core without the star, okay? So in our studies in the first decades of the 2000s with Eric Ito, we studied, in fact, this sample of starless cores. And it was obvious that you can divide the population of the starless cores into main categories. So we typically tend to call all the cores with no stars as starless cores, but we can actually, if we look closer, some of them are actually different in a sense that they look more centrally concentrated, and they have also evidence of infall motions in the central region. So some of them you can immediately say, okay, this core is going to form a star. So this is an example of the two. These are prototypical cases. So one is B68. You must have seen these somewhere. There are pictures everywhere. You Google B68, you see this Alves et al. 2001 beautiful near infrared and also optical picture, which is, this is a globule that is very close to the galactic plane. So you see lots of stars in the background, and of course where there is the globule, there is nothing because it's in the optical, is very dark. But you can see here the density is not very high. So the central density is actually has a very strange shape, and it's most likely in hydrostatic equilibrium, but it's kind of oscillating. And the density doesn't reach more than, say, much more than 10 to the 5 per cubic centimeter. The temperature is typically 10 Kelvin. This is the dense core temperature. So when you look at the spectral lines, you see profiles, in fact, that are consistent with oscillations. And this was a beautiful work done by Charlie Lada and collaborators in 2003. When we get into this starless core with the central density enhancement, we are in the pre-stellar core regime. And here the difference is that the central density gets higher than 10 to the 5. We typically see 10 to the 6. And what we see is that the temperature keeps decreasing. So if you go to higher and higher densities, the central temperature drops to about 6 Kelvin. Now, if you look at the spectral profiles of the high density tracers, so what you typically see, you see infall asymmetries. So this is a spectrum that has a blue peak brighter than the red peak, and you have this, you can reproduce that if you assume that you have contraction motions. So this is just to tell you that indeed, not all the dense cores are the same, and starless core like B68 may also expand back before forming a protostar. This is the work that we did in 2007 to see, actually to measure the temperature inside this pre-stellar core, one pre-stellar core in Taurus. And you see that using the VLA, the red dots here, you have rotational temperature. This is the rotational temperature of ammonia. We use the ammonia 1,1 and 2,2 lines to measure the temperature. This is a very famous thermometer. So you go down to 6 Kelvin, and you notice that only with the interferometric data you can see this, because if you use a single dish, you basically you miss what is going on in the very center, because these regions, as I said, are centrally concentrated. So you dilute the molecules emission that comes from the very center, which is very cold. These 6 Kelvin temperatures, this very low temperature, they favor two important processes. One is the freeze out of the molecules. In fact, we see evidence of that. I'm not going into this because this is more, say, the astrochemistry part, but I wanted to mention because I think this is still very important, because to study star formation, we need to study these molecules. So you don't want to use CO actually to study the central region. What happens in these cases is that we have an enhancement of the fractionation, so of molecules that contain deuterium. And in fact, we use them to actually study the kinematics and the structure. So this is this picture here is just a sketch to say that in these cold regions, so just before a protostar is formed, you have the dust grains that are covered by thick icy mantles. So basically you have already a lot of ice that probably will actually contribute to the formation in later stages when the protoplanetary disk will be formed, as we will see, to the formation of planets and also giant planets. Okay, but let's not get too advanced. My last slide for the little introduction is we need to remember that the molecular materials, molecular clouds, and also of course in the atomic phase, but all our galaxy is basically magnetized. So we can't forget about magnetic fields. We cannot forget them when we make models, but also when we do we try to connect the chemistry with, star formation and etc. Because in fact, the magnetic field can affect a lot, as we will see, the collapse and the also formation of protoplanetary disks. So this is it's a beautiful image. I think it beats some of the most beautiful pictures I've seen, also from the point of view of artistic. So it's the magnetic field in our galaxies is seen by Planck, and we are here at 353 gigahertz. Great. So as you see here, I have a long list of things, but of course we will not go too deep into any of these. I will give you, as I said, some ways of quickly estimate things and understand why maybe magnetic field is important, or pressure, thermal pressure. So without going into too many, equations and something simple, back to the envelope calculation. So start with some gravitational collapse. Of course, that's important. Fragmentation, when do we stop? Why there is no infinite fragmentation until atomic scale? So this is something that we will talk about. Disk formation, the accretion disks, just this, as you see, already preparing for tomorrow for the planet formation. But of course, this is important also for the protostar because it is accreting through these disks. Then I will say a few words about the hydrostatic cores, and then finish, if I have the time, with protostellar feedbacks and how they affect the surrounding of the cloud. So if you have any question, you just stop me. Maybe, I don't know, somebody turn on the microphone. So, and I also put some references, because of course, if you want to go deeper and you want to see what is through the lines that I'm going to tell you, I strongly suggest the specific chapters of the Staller and Palla book, which is 2004, so it looks a bit old, but actually the physics is the same. There is not much change in the physics of magnetized clouds. Of course, observations have changed, and maybe we have learned different things, but the main equations are still there. So the gravitational collapse part, I start with this beautiful image that was taken by the Spitzer Space Telescope. On the left, you have the visible image of this. It was considered a starless core before Spitzer. And you see here the dark part and the stars in the background. But when Spitzer came on, it was sensitive enough to actually see that in this part of this starless core, there was a very tiny low luminosity object. This is an example of the so-called very low luminosity objects, or bellas, that in fact it was not seen before because the previous infrared telescopes were not so sensitive. But just to tell you that this is another example, and say it's a witness that the star formation really happens in these dark regions. So the physics, it's very complex because you have to be able to really follow the whole story from cloud to star. You have to be able to go from size scales. This is actually the B68 globule that I was telling you before, that you see in the visible. So the size, so you have to go from sizes of about 10,000 astronomical units, or in meters. I don't know which units you use. Everywhere I go, people use the SI standard international system or the CGS. So I will have a mixture to confuse you, but actually also to try, to make these unit conversions. It's always good to play with these things because it's always easy to make mistakes. So I will put different type of units here and there. So the size goes from 1.5 10 to the 15 meters for the Bok globule here. You have to go down to 7 times 10 to the 8. And this is the size of our sun. This is what really have to happen in this region. So, and what about the density? Well, we start with something that is of the order of 10 to the minus 16 kilograms per cubic meter. And then we arrive at the sun, which is actually quite large here. So you see that the orders of magnitude are huge. So orders of magnitude of density and size, and also temperature, everything. I mean, all the physics is going to be in here. Is going to be an enormous problem, an enormous and challenging problem to try to understand how things are actually forming. But there have been some studies, and we are on our way to at least put pieces of the puzzle together. So the main thing that one needs to understand, and these are really the kind of astronomy 101 for star formation. So is what do you mean by hydrostatic equilibrium? What is the virial equilibrium? What is the collapse criterion, Jeans mass and free fall time? And we will arrive at this, for example, Jeans mass and free fall time with very simple equations without going into complex mathematics here. There is no need. especially because, you know, if sometimes you find something in the literature, you don't want to spend half an hour to try to just order of magnitude calculation in your head, and that's enough, okay? Of course, if you are studying star formation in particular, you want to go a bit deeper than this, but anyway. So these are the main equations that you want to know. And of course, here we are starting without magnetic field or, for example, turbulence that in any case you can add, for example, the turbulent in the velocity component with no problem. But okay, so let's start with the simplest system. So you have an isothermal sphere in hydrostatic equilibrium. And what you have here, you have a cloud with, say, the equilibrium is maintained simply by this balance between the self-gravity and thermal pressure. So you have 4 equations that you need to know and to write down if you want to write, for example, the Lane-Hamden equation or something similar that describes the structure of your cloud. So the hydrostatic equilibrium equation is this one that connects the gradients of the pressure, rho is the density, and this is the, of course, the gravitational potential, phi g, and this is the gradient of the gravitational potential. So P can be written, this is the very important formula to, in a sense, remember. So is the pressure is the product of the density times, here is the sound speed square, because we said that we are just considering the thermal speed. And then here is the Poisson equation, where you have, again, the gravitational potential, the density, the rho density, this is in gram per cubic centimeter. And then here is our G constant, gravitational constant. And this is the expression of the sound speed. Okay, so basically this is your equation that you want to play with. And these are all the definitions of the terms that are in here. In the expression of the sound speed, where you have the Boltzmann constant, the kinetic temperature, and the mass of the proton or the hydrogen atom, here you have the mean molecular weight, because of course, if you are in atomic cloud or molecular cloud, this will change. So in a molecular cloud, taking into account that you have mainly H2 and helium and some heavy elements, it turns out this number to be 2.4, but you can also do that as an exercise for yourself. So let's see if we arrive then at very simply at this expression of, say, the Jeans criterion. So to do that, the easiest thing is to consider a shell of mass, in this case, dmr. So the mass, of course, is within a radius r here. Then the equation of hydrostatic equilibrium, basically, if your cloud is spherical, it reduces to this very simple expression here, where you have the pressure term and the gravitational term on this side. So 4 pi r square for the spherical cloud. So then what you need to know to actually go toward the Jeans criterion is just how to define the volume. I'm sure you know how to define the volume of a sphere. You then substitute this VDR in the previous expression, and what you have, so now you get rid of the 4 pi r square in the other expression. I'll just show you again. So remember, we start from here, and then you go here. So you have now the volume. So you have 3 times the volume at the radius r in the PDR. And then this must be equal to minus GMR dmr over r. You see, I mean, careful with the powers. So the r has cancelled. I'm not going into all the passages. I'm not in front of a blackboard. So, but you know, I think here there are enough passages that you can understand, and you can also see again these lectures if something is not clear. So now we have to integrate from the center of the cloud to the surface. So from 0, pressure at the 0, so at the center, and the pressure at the surface, these 2 quantities, okay? And the MC here is the mass of the cloud, the total mass of the cloud. So you immediately recognize something here. So this is the total, now it becomes, this is the total gravitational energy, which is typically denoted by the symbol big omega, because it's a little bit confusing because we also use omega for the angular velocities, but let's now focus on the virial theorem here, which we will arrive in a minute. So here we have omega on this side, and here we have this volume times the pressure. This integral here, you can actually solve it just using the left hand side. So basically you just need to integrate by part. So here you can, the left hand side here can be rewritten in this form here. This is the general expression for the integration by part. So if you do that to this expression here, you get now 3 times the volumes of the cloud, the surface pressure, minus, see here, x is your, here is the pressure. So you have minus 3 integral between 0 and Vc of the pressure times in the V. So you have the integral in the volume of the pressure. Okay, so this is just the integration by part. I rewrite the expression here just to make sure that it's not lost immediately and to follow. So now the next step to remember, and I think this is again very simple, everybody knows this, is that the connection between the pressure and the thermal, the kinetic energy density, which is symbolized by this letter U. So we know that the U is equal to 3/2 nkt. And remember that P, we already saw that it has a very similar expression. We saw before that is equal to rho times the sound speed square, and I gave you the expression of the sound speed. So if you put this expression of the sound speed in here, and you know that rho is actually n times the mass, basically, so you will end up into this expression here. N is the number density of particles per cubic centimeter. So you see that now you can actually write P equal to nkt, which is very easy to remember, and it's very important because it connects with the number density and the temperature, which are two things that we typically measure. So you can immediately measure the pressure of your cloud, for example, if you know N and T. But this is going a little bit beyond, so just focus on this. So P is equal to nkt. So we put this expression into this integral here. And you have that P is equal to 2/3 U, and this is how the 3 here goes away, and you're left to 2 integral 0 to Vc of the U in the volume. So this is the integral of the volume of the kinetic thermal energy density. So when you integrate, it becomes the total, say, energy density, which is typically, you use this capital U to consider that. Right, so we have to put everything together now. So this is of course, the volume of the cloud is still this 4/3 pi r cloud cube. And the total thermal energy, we just saw it. So we put these things together. And you see that the equation that we start with, so this hydrostatic equilibrium, equation, it ends up with these simple terms. So we have 3 times the volume of the cloud times the surface pressure minus 2 total kinetic energy density, and equal to the gravitational term. So we have a pressure term and a gravitational term. If we rearrange, we can just have these 2U plus omega equal to this value. So now you can see immediately that we are at the virial theorem, because if we assume that it's typically done, in fact, that there is not surface pressure, so we are just assuming that there is no surface pressure present, this equation becomes equal to 0, and then you get to the so-called virial equation without magnetic field and other complicated structures. And of course, you can also rewrite these terms in terms of the cloud pressure and the cloud volume. So 2U is equal to 3 times the cloud pressure and the cloud volume. This comes from the previous equations that I show you, and the connection between pressure and U. And then for the omega, if you want to actually have a value that is related with to the mass and the radius of your cloud, you simply have to do the integral that we saw before of this gm in dm over r. And if you put here, instead of mr, your mass of the cloud as a function of radius, which is in this case a sphere, but of course you can use also other shapes, you have your further pi rho r cubed, and then you have dmr, so you have to do the differential of that, and you end up with this equation here. So the gravitational say potential term here is for a spherical cloud of uniform density is minus 3/5 gm squared over r. Right, so you can measure masses, you can measure radius, so you can actually estimate immediately from the observations if your cloud in absence of magnetic fields can collapse or not. Of course, if the two terms are equal, it is in hydrostatic equilibrium. If the pressure term is larger than the gravitational term, of course, you have in this case most likely a dispersion of the cloud, expansion. We see actually examples of that as well. In the reverse case, gravity wins and you have contraction. And now we arrive at the Jeans criterion, again, without doing any perturbation analysis and very simple equations. Of course, we are assuming a lot of things. So, but here what we have to do to arrive at the Jeans criterion is simply starting again from our virial theorem. So you have here the gravitational term now that is larger than the pressure term. In this case, then your cloud is contracting. So now the question that we are trying to answer here is when this happens, when this part here is larger, what is the mass of the cloud above which the cloud will contract? All right, so what do we have to do here to actually have something that relates with the physical parameters like temperature and density is try to remove, for example, these terms of the pressure. We already know is nkt, but you can actually write it also with the mass of the cloud. Remember the connection between rho in grams per cubic centimeter and n in cubic centimeter. So there is a mass involved in there. So you can just write the pressure as mkt divided by mu, the mean molecular weight again, mh, which is the mass of the hydrogen atom, and the cloud volume. Your cloud radius, you can actually rewrite using the expression of the mass of a spherical cloud. You just take the radius explicitly out of the equation and you have this simple expression. So you put these two inside in here, rearrange, isolate MC, the mass of the cloud. So the condition for collapse is that the mass of your cloud has to be larger than this term here. So we have lots of constants here, you see, but what's important is the temperature term that now it goes to the 3.5 power, and the density term, which now goes to the -1/2. And this is the only thing you need to remember. So the temperature, so the mass of the cloud, if it is larger than this, it will indeed collapse. But for example, if you have a temperature that is increasing, then it may become more difficult, you know, you can get actually equilibrium. If the density will increase, so this whole thing will get smaller, the MC will also decrease, which then what happens is that you will actually end up with contraction and fragmentation. So this Jeans mass, now I can start to call it the Jeans mass, becomes smaller and smaller. So in fact, I mean, this is when you have equal here, you can call this as the Jeans mass. If I take away all these, constants, and I write it down with, say, astronomer terms, this equation boils down to this simple expression. So the gene's mass is about, say, 10 to the 5 times this important power loss, temperature to the 3.5, divided by the molecular weight to the square, and n to the 1/2. And this is in solar masses. So now let's look at what we have in our say clouds, so what we typically measure. So if we take a typical dense core, typical temperature is about 10 Kelvin on average. The densities, okay, now I put it in meter cube per meter cube, so it's a little exercise. It's 10 to the 10 per meter cube. So the mu is 2.4, as I already said. So this translates to a gene's mass of about 5 solar masses. Actually, this is not so different from what we measure for these dense cores that we find, say, nearby clouds. So it's probably a bit higher than, say, on average, but it's not too far off. However, if you look at the GMC, so the giant molecular cloud, with the temperatures on average of 15 Kelvin, and densities, average density is a bit lower than that, so 10 to the 8 per cubic centimeter, this translates to a gene's mass of 100 solar masses. Now, this is extremely lower, much lower than the mass of a giant molecular cloud. I told you at the beginning that the typical masses are larger than 10 to the 5 solar masses. So if this is the case, and we just did it, it is the case, then what's going on? I mean, this giant molecular cloud should be collapsing and making stars like crazy, but actually we don't see them. So, of course, this tell us that this study here, so this simplification to arrive at the gene's mass, which of course also genes himself did not consider magnetic fields, so this is really just considering thermal pressure and gravity, it's not enough. So that definitely there is something else that holds on these giant clouds, because, you know, as you know, the efficiency of star formation is very low in our galaxies, just a few solar masses per year. So most likely magnetic field and turbulence are needed, in fact, to slow down. Another back of the envelope calculation. So we want to see if gravity or pressure becomes, say, more important once the cloud collapses. Again, you know, talking about just thermal pressure, which is not a bad assumption if you actually just focus on dense cores. I just show you, in fact, that the gene's mass is not so different from the dense core mass. So if you're just focusing on dense cores, it's not too bad to actually consider maybe just the thermal pressure, because we see that also from the lines of these the molecular lines tracing these dense regions, there is not much turbulence at all in here. Of course, there are magnetic fields, but say there is no much extra, say, motions that say slow down the collapse, except of course for the magnetic field. But so just considering the gravity and the pressure, you see from here that gravity will increasingly dominate. So if you have just thermal pressure, there is no way you can hold your cloud, because in fact you can see this because the gravitational force, as you know, is proportional to r to the -2. The pressure is proportional to area, sorry, the force pressure is proportional to the pressure times the area. And of course, the pressure, because the pressure, you can write it down like this, and you have a rho here, which is actually centimeter to the -3. So this is proportional to r to the -3. So you see that the pressure force is proportional to 1/r. So you see that the gravity wins eventually anyway. So there is no way that the thermal pressure, once you start the collapse, will actually halt the collapse. So this allows us to actually arrive at the free fall time and do it in a quick way without having to remember the formulas. The expression where we arrive at, it's slightly different, but not very far off the actually more detailed expression. So it's always useful for orders of magnitude estimates. So again, ignoring pressure, you just can write down the equation of motion for a thin shell of your cloud, which has a radius of RC. So you have your acceleration term. This is the gravitational force. So you put here the values of, say, considering, say, the mass and the density of your cloud, etc. So assuming, so here I say note that, but actually it's assuming that the mass within the radius R remains constant, which is an assumption, because in real life, maybe this is not really true. You still have accretion from the cloud onto the core, which is really important, but for the moment, let's forget about all these complications. So we approximate this equation of motion, assume that the acceleration is constant. So you have your acceleration here given by a constant term, where you put actually the radius of your cloud here. So if it is constant, it doesn't matter where you are. And so just doing that, you basically arrive at the free fall time. So here you then do these very bad things that mathematics people hate, but you know, you have here a square time, and here a radius that cancel out with this radius here, and you end up with a expression of the free fall time that in fact you see contains only as a physical quantity the density. Here is the density in grams per cubic centimeter. Great. So this is the more, how to say, accurate free fall time expression. I never remember this free fall time expression with all these numbers. I mean, of course, you can memorize the final output here. So 5 times 10 to the 10 years, and then you divide by the square root of the mu times n. You can also put the mu actually in here in the number. But in any case, so to form, for example, a 5 solar mass star, so from a 5 solar mass cloud, assuming that all the mass goes into the star, the free fall time here becomes about 3 times 10 to the 5 years. Quite short. So it looks, you know, it's just a few times, say 300,000 years, you form a star. Of course, again, very simplified assumption, but this is what we typically consider as the dynamical time of your cloud. Then, of course, in reality, it takes much longer to form actually a star for many other reasons, including also, you know, the presence of a magnetic field, but also the fact that the star actually will stop accreting mass at much later stages. But in any case, this is our dynamical time scale. And of course, if you have less dense region, the time to form the star will be longer because of this square root of 1 over square root of n dependence, and shorter for denser region. This is just a self-advertisement. It's the work that we did last year using actually ALMA and the ACA. And in this case is one of the pre-stellar core that we have studied, to just see the central region that we ended up calling it the kernel, because this is already a core, so I cannot say core of the core. So we want to see the central region where actually the future stellar system will form. The central region in the continuum, it's very tiny. It's basically of the order of 1,000 astronomical units. The whole cloud is actually more than 10,000 astronomical units. So ALMA, if you just look at the main array, will get rid of all this extended emission, and you just see the centrally concentrated region. And you see here that it's very tiny mass. So the whole cloud, the whole dense core, the whole pre-stellar core is about 8 solar masses. ALMA gives us only information about the central 0.1 solar masses. So well, first of all, we need ALMA to do this type of observations. There is no other telescope that can see the continuum emission from these, say, starless regions. It's so cold and tiny. And then also it says that, you know, mass must still keep accreting on it to actually form something that is of the order of a solar mass. So we are really in the early stage here of conditions. And there was also some hint of fragmentation, but we couldn't really say we were not so much significant. But if this was significant, this was a great result, because it was telling us that you can actually do fragmentation during the process of core contraction, which is not at all obvious. You know, when binaries form, many people think that they are formed maybe in the protoplanetary disk, fragmentation of the protoplanetary disk. Right. So I would like, well, actually it took probably longer than I thought, but if you have some questions now, you can tell me, or if you want to have a little break, I mean, I'm fine, but if you have one or two questions now, it'd be good. If not, I assume it's all very clear. I take it as a compliment.
All right. It is actually very clear, but
okay, very good. So I'm going ahead, and of course, yes, I forgot to say, if you have questions also, you know, tomorrow, say, sometimes also for me it takes a while to get the question, but you know, I keep thinking about things. So if you have a question, you can freely send me an email. That doesn't mean that I will answer immediately, but you know, I will answer. So just send me an email. Great.
Listen, Paola, are you about halfway? Because then we may take a short break.
Maybe I could go to this fragmentation part, and then we take like a few minutes break, if that's okay.
Yeah.
Because we are now in this part of getting smaller and smaller, so I'd like to finish this part here. So actually, I included, as you see here in this fragmentation part, some things that I'm sure probably Cecilia has already mentioned to you. So the heating and cooling mechanism. So I will not spend too much time on those, but I just wanted to review a little bit just to make sure it's clear what I'm talking about. So basically, I wanted to understand when this fragmentation stops and what is actually causing the fragmentations to stop. So we want to see again this expression. This is the cloud mass. We said if the cloud mass is going to collapse, it must be larger than the Jeans mass. And remember also the expression. This is the full expression of the free fall collapse that is proportional to the rho to the -1/2. So, and the Jeans mass is instead proportional to T to the 3.5 and rho to the -1/2. But these are the only things, say, to remember. Then we have to see what happens when the clouds start to collapse. Is this an isothermal collapse, or you know, is the cloud heating up? It can't really cool down, so the only thing it can do is probably heating up. Let's see, because you know, we don't know. We can actually be open. We can do anything. So if the core temperature remains constant, as I wrote here, during the initial stages, what happens is that the Jeans mass will decrease with time, because of course you have the density that is increasing. Okay, so let's look at the cooling processes. The cooling time is given to you if you divide the thermal energy in your cloud. This is U, the famous U that we saw before, now in units, joule per cubic meter. And then you divide that by the rate of loss of thermal energy, which is typically given by this term lambda, capital lambda. Now you see joule per cubic meter per second, so this is a time. The ratio is indeed a time. So you can use the equation that I show you at the beginning on 3.5 mkT divided by lambda to actually find out. And this is part that I will go a bit quicker because I hope has been covered, or anyway you know about. If you don't, you just ask me. So main heating process. So you are in a dark cloud, and if you're in a dark cloud, it's really dark. You don't see photons, many photons around, especially the UV photons that are absorbed by the dust grains. There is a little bit of a UV photon, but very, very tiny, and it's really dark. And so these photons that are inside your dark clouds are not able to actually heat up your cloud. The only way to heat up your cloud is actually through cosmic rays. So cosmic rays As you probably know, they are accelerated, especially the most, say, energetic ones, accelerated by, say, supernova event in shocks. And what happens here, so here you have a magnetic field line. So when you have, of course, these are all ionized particles, either protons or nuclei of heavier atoms or electrons, and they, of course, gyrate. This is the radius here, the gyro radius, etc. But you know, all things that have been sorted out since many years, and there are books where you can actually look into that. The important thing is that, for example, if you have a proton, cosmic ray proton hits the H2 molecule, because that is the most likely things that is going to happen in molecular cloud, given that H2 is the most abundant molecule, it will produce H2 plus electron, and of course, the proton still continue to go with the leftover energy. So now what happens is that, here I actually added something. So I mentioned that the cosmic rays are produced by supernovae event, but there is more and more evidence that actually the low energy part of the cosmic rays can be accelerated most likely locally by actually protostellar jets. And this was work by Marco Padovani, who works in Arcetri, and you can have a look at that to see his conclusion. And there is also some observational evidence. So let's see how much energy is given by these cosmic rays. So we have electrons that are produced. These are the so-called secondary electrons, because are produced by the collision of this primary proton here that is from the cosmic rays. So these are the secondary electrons that actually gives this heat to the cloud. And in which way? So the gamma, which is now the heat term, is proportional to this so-called ionization rate. That is a probability per unit time, and is of course related to the flux of cosmic rays. And we know in the interstellar medium, values between 1 and 10 to the minus 17 per second. Then of course you need this energy provided by each cosmic ray event, and then you multiply that by the number density of H2. So when an electron, so how electrons actually provide this heat? So the secondary electrons can dissociate H2 molecules. So they actually hit another H2 molecule, they dissociated, and the hydrogen atoms that are produced in this way contain some extra kinetic energy, because they are not using the whole energy to dissociate the H2 molecule. That is about 4.5 electron volt dissociation energy, but you can have like several MeV of say energies from the original protons. So on average, you can see, if you consider, say, the spectrum of the cosmic rays, again, I don't want to go into the details, but you have that the energy input for that goes into this, say, heating terms from the cosmic rays, about, say, 7 electron volt. So if we include this delta E in the previous equation, we get something like of the order of a few times 10 to the minus 25 joule per cubic meter per second. And now is the question for you could be, what is the dominant cooling agent in molecular clouds? Now I don't see you, so I cannot point to any of you. And but I think from what I said and the maps that I showed at the beginning, should be obvious that the main coolant, at least in the dense cloud, in these regions where the densities are, say, of the order of 10 to the 4, or maybe 10 to the 3, 10 to the 4 per cubic centimeter, is CO. CO is very easy to detect. In fact, you have seen the whole map of the galaxy. And the energy, of course, this depends, so the cooling of the CO depends on several things, in particular on the number density of the CO molecules. But in a molecular cloud, you can assume that most of the carbon is actually in CO. So you can have a easy way to actually estimate the number density of the CO molecule. Also the energy of the transition, but we typically consider the low energy, say, as the easiest to detect and also to measure. So this part is just for So not even for here, I'm not going into the details of this, but it's just to make sure that you understand the next slide. So here I just listed the definitions of very important, so fundamental quantities like this one, Einstein coefficient for spontaneous emission from the upper to the lower level, the collisional, the excitation coefficients. These are the only things we need to know, basically for the rest. And then, of course, is the excitation temperature for the, say, population of the various levels. But we can assume for CO that we are in a local thermodynamic equilibrium. So kinetic and excitation temperature are the same. So if we look, you see here now, if we wanted to understand what is the cooling for cooling rate for the CO molecule, you need the Einstein coefficient of the transition 1 to 0, the de-excitation coefficient, collisional coefficient from 0 to 1, because in these conditions of, say, molecular cloud, where the density is higher than the critical density of the transition, basically each excitation will be followed by a collisional de-excitation. So you will, the collisional de-excite the molecule before the molecule will actually radiate back. So in this case, it's very simplified. You can simplify the expression of the cooling, and you just need the number density in the upper level, the Einstein coefficient that you can find in a tabulated form, this extra energy, and you get something that is of the order, in fact, of the heating time. So this is good because it's some kind of, there is some kind of equilibrium between the heating and cooling. But the main question we had was actually, can we assume that the cloud is actually isothermal during the collapse? So let's go back to our cooling time. So our cooling time is, you remember, 3.5 nKT. So this is the internal energy, the U. Lambda is the cooling from the CO. So putting together the numbers, so you have something like 7 times 10 to the 3 years, assuming that you have a typical, say, dense core density, say, 10 to the 4, something like that per cubic centimeter, or 10 to the 10 per cubic meter. So if we have to compare this with what? Well, with the dynamical time scale. The dynamical time scale is the free fall time, which is actually 3 times 10 to the 5. So you see immediately that the TC, so the cooling time, is significantly smaller than the free fall time. And of course, if you have magnetic field, this sign here should be much, much smaller, because then it gets even longer to collapse if you have actually magnetic field. So you can easily assume that the collapse is initially isothermal. So as the core collapses, the density increases, the temperature remains constant, so the genes will collapse, the genes mass will decrease, and this means that you expect to see fragments. So you have the cloud that fragments because you have the gene's mass, the mass of the cloud that is larger than the gene's mass. Then you look at the smaller fragment, it continues to fragment, and so on and so forth. So you see this in observations. This is a beautiful paper actually from 2004 from Boiter and Schilke, where they actually see that going at smaller and smaller scale, they see more and more fragments. But we know that it can't go on forever, no? Because otherwise you can't even form a star. Everything should be like a little planet floating around. So this is the question now that I really want to try to answer. So what stops the fragmentation? And for doing this, I would like to, so we have to consider a few things. So you can assume that your cloud becomes isothermal, and stays isothermal actually during the time of collapse, as long as your cloud can radiate the energy that gains while it is contracting freely away, okay? So this means, in technical terms, that your cloud remains optically thin to the radiation. Is this the case? Okay, so let's see. because if the cloud becomes optically thick, this is a problem in a sense, or in any case, this is actually not the problem. This is a good thing. This is why there is not this runaway fragmentation. It can no longer cool effectively. So you have actually the temperature that is increasing. So the jeans mass is increasing, and then you get, more, say, larger regions that can get stable. So the question now, instead of saying, how the fragmentation start, is, does the optical depth increase? This is now the question to answer. Let's look at that. So from the radiative transfer equation, you probably recognize this. So you know that the optical opacity, the optical depth here can be written as the product of the size of your region, delta S, or the radius, and rho K, so rho is then, again, grams per cubic centimeter, is the density of your region, and kappa here is the opacity of the dust, because of course the opacity is mainly through the dust. So tau is proportional to the number density, because rho, remember, is number density and then times mass, and delta S, okay, is our say radius of the cloud. You can rewrite the radius using the equation that we found for the jeans mass, and you end up, so you just put the dr on the left side, and if you again put down the numbers for the various constant, you get that the jeans radius now, because this is coming from the jeans equation, so the jeans radius is about 10 to the 4 divided by nu, the mean molecular mass, times the square root of T over n, okay? So if you put this in here, you see that tau is proportional to the number density, square root of the number density, if the temperature is constant again. We are assuming here, say, constant temperature, which is the case when we have the initial, collapse, as I demonstrated just 2 minutes ago. So tau increases as n increases. So the tau is getting larger. So this means that eventually you get to the point that your fragmentation is stopping. So what is then the smallest mass of a fragment that you can produce? Of course, it will depend on the environment, on the number density, on the temperature, but we can actually express here, find a number for typical values. So here, for example, how do you do that? So how do you set this problem if somebody asks you what is the mass of the smallest fragment? So here what you have to do is to consider this contraction motion. So you have to have the rate of gravitational energy, rate of gain, as I wrote here, in gravitational energy. So this is the gravitational energy divided by the free fall time. This is dynamical time. So this ratio should be about the same. You can equate that to the radiative radiation loss. So here you have the Stefan Boltzmann constant, and you recognize the sigma T to the 4. And then, of course, you have your sphere for pi r squared. So you then, to answer this question here, you just need to use the equation that we derive, or say the expression for the free fall times, if you want it to be precise, the formal one. Then remember that the mass is equal to 4/3 pi rho r cube. So you have also an expression for the r. So then you can get rid of r here and arrive at the mass of the fragment, which is equal to this expression here, where you have some power of the temperature and some power of this mean molecular mass. So if you put here, for example, this is just an example, you can put whatever you want to make actually changes in environment, etc. But if you have a 10 Kelvin gas, mu equal to 0.4 for a molecular gas, your mass becomes 0.02 solar masses. So you're actually changing these parameters T, but also mu. If you want, you can do maybe, I don't know, some more molecular, atomic and molecular or whatever. You can play with these things. you can actually find that your fragment can be as low as the lowest mass star that we can actually find in our galaxy, for example. So we can actually explain, in a sense, with this simple mechanism, how to make all the different stars, super simplified, of course, but you can explain why we have all this population of stars. So a little summary, and then we can stop for a few minutes if you wish. And so the initial collapse here, remember, is isothermal because the cooling time is less than the dynamical time. And then, of course, if your Jeans mass decreases, you can have smaller fragments. So you have fragmentation, fragmentation of a cloud. And then you can have runaway fragmentation, but up to the point, because you remember, we have the optical depth of your cloud that increases with the density, with the square root of the density. So this means that at some point, this fragmentation has to stop. And with that, you can explain the range of stellar masses that are observed. So I stop here, and either you ask me questions or